Hi, this is Bill Foote, and this is Stats 1. We are up to Lecture 5, and we're in Part 1 of Lecture 5. This may go into a second part, Part 1A and Part 1B, perhaps. We'll see how it goes. We're working with what I call Gauss's robots. They're robots, and they're made by a guy by the name of Gauss. We'll go into that in just a second. We're still always following, as we have in the prior 4 lectures, our analytical workflow, a process that begins with posing a question, forming hypotheses, sampling data, and perhaps going back and forth between formulation of a hypothesis and sampling of data to make sure we get our hypotheses relevant to whatever the sample is. And then we count. We count how many ways the sample of data is compatible with the hypotheses that we have formed. Finally, we perform some inference. Now, inference means we have made a logical set of statements, and we are still always looking for the most plausible hypotheses. Where later on in future lectures, we're going to expand that idea to look at really get into the range of plausible hypotheses. And that process will actually begin next week in Lecture 6, given that these are weekly lectures. What question are we going to pose today? Well, most students in most schools understand their grade point average. And what we're going to do is ask a very straightforward question. What GPA, what grade point average, might I expect given a low and a high level of uncertainty about my GPA? Well, low and high uncertainty probably means something about the range. This is a standard performance question anyways. There are some environments and behaviors in which things were not so uncertain, things that are much more uncertain. So we're actually double barreling a question here. It'll have 2 aspects to it. One is the level of performance, and the other is the range of levels of performance. So we have 2 things we have to worry about. So we'll just write up a little something here. The question is, what can we expect our GPA to be given, well, a range of GPAs on the one hand in different environments. On the other hand. So that's what we're looking for. And just let me move this out a little bit. This question over here, not out of the way, not forgotten, because now we need to form some sort of hypothesis. We know what our GPAs look like. We can say we get a sample first and then form the hypotheses, but the question basically gives us 2 kinds of terms. And these are very familiar to us from middle school and high school statistics. What is an average? What can I expect of my GPA? That's an average. Some expectation is the average. Well, that's also given 2 different environments. And so then the question is, given whatever data I have, my hypotheses will try to detect the level of the GPA on the one hand, and the kind of environment that GPA might inhabit. We're going to pose two different environments. We're going to say we're going to have a range of GPAs in here that we're going to measure with mu's or means, and we're going to look at those GPAs relative to two possible levels of environmental uncertainty, the environment of taking courses or doing a job, getting an appraisal of those courses of that job. The standard kind of performance that we would expect, and we're going to formulate multiple levels of mu. We're going to go on a 4-point GPA scale. That's typically what a GPA scale is. 1, 2, 3, 4. 4 being the best, 1 being really not, and you can technically get a 0, but we're going to go from in this particular case, we're going to go from 2 to 4. So we're going to start off with 2, we're going to go up to 2.5, 3, 3.5, there we go, 3.5, and 4. Let's get rid of this one here. There we go. So that's going to be our 5-point mu scale that we're going to attempt to depict what's the best one there, with defining that inferentially as the most probable, most plausible. And we're going to have two levels. We're going to have one regime is going to be half a grade point average, half a point, and we're going to double that to make the other one much more uncertain. So now we have levels of hypothetical values that make some sense. Now, one way we can put all of this together in a way that we have used before is to, over here, we have our hypothesis. 1, 2, 4, 5. We have mu's. I'm going to put these in all green here. And we have a mu that can go from 2, 2.5, 0.0, 3.5, 4.0. And now we have the problem of two different environments. Well, one environment would be 0.5. And just keep it the same for each of these different levels of potential, hypothetical, conjectured grade point averages. Well, that's one environment, but there's also another environment, and this is where we have to get a little bit creative. We have to expand our notion of hypotheses to have a 6th, 7th, 8th, 9th, a 10th hypothesis. And now this will be defined by a new volatility environment. How volatile is your performance? Plus or minus a whole grade point here. We're just thinking about this. We haven't actually measured anything yet. And for those, we still have to go back and look at the range of mu. And going from 2.0 2.5, 2.0, 3.5, 4.0. And we say, okay, this is fine. This is fine. We have an idea here of how things are going to work. We have 10 hypotheses now. And each one of these pairs, the 2 and the 0.5, is of course different from the 2 and the 1. They're in different regimes. We do different sales regimes where we're in a low competitive environment versus a highly competitive environment. And we might look at our revenues from that point of view, our average revenue, our revenue growth under 2 different customer market environments. We might do the same for different environments for production and dealing with vendors and buying various materials from vendors, different environments. And this is a nice, neat, simple way of doing that. We always want to specify. Now we have 10. Hypotheses, and for a proper, you need to have 1/10 is the probability of each one of those hypotheses. And I think I'm going to make hypothesis number 8 here. Special attention. Okay, now we have formed hypotheses. Now we might have to reform these in some of their details, having looked at a sample. Now, what sample are we going to use? That's the second part of the story. And the data that we could be using for that, we could look at, let's say, 3 performance periods. Now, in education, higher education at least, performance periods are defined as semesters. So 3 different semesters. And so one of them might be the 3.5, pretty high grades. Another one might be 2.5. Another semester. And the third one might be a 2.0. It didn't go as well as planned for one reason or another. A little data here. See if we can make any headway with this. Now, we have 2 parameters, and now we want to use some way of saying what is the likelihood of seeing a 3.5 given a mu and a sigma. That's always what we've been doing, and that likelihood is the probability of seeing one of these, I'll call it a G, one of these GPAs, given a particular mu and a particular sigma, a level of performance and a performance environment. One is less volatile than the other, one is more volatile than the other. Still want to do this. Well, it turns out there is a distribution we can use, and we've already kind of prepped up on this distribution. And it's going to be called an error distribution. An error function is actually what one of its original names was, and it will be the Gaussian distribution, named by Carl Pearson at the turn of the last century, 1900. The normal distribution, and supposedly he regretted calling it normal. Normal has some very interesting ideas in mathematics, what it means. We, in effect, have normalized these likelihoods times their probability of an hypothesis. So let's see where we can go with this. finally it comes back to us. So we have our sample. Here's Carl Friedrich. Let's see if I can expand this. There we go. There we go. This is a nice portrait of him in 1840. And he's responsible for quite a bit of work, astronomical work, work in magnetism and electricity, physics, surfaces, algebra. He really studied these in great detail, but he also understood practical things like data. I think he probably had to earn a living at some point. And one of his livings was working for the Kingdom of Hanover in Germany on a geodetic survey, trying to get that right. And actually came up with a fairly decent approximation for a lot of different physical objects, one of which is the Earth itself. We're actually building robots, and here is my Gauss's robots. This is probably Carl Friedrich right here. Okay, that doesn't look too happy. He's created multiple ways of dealing with data, and we're calling those robots. We're going to continue to call those robots because they are machines that will do exactly what we tell them to do. We put in a number, we can expect a particular kind of number, an even level and range of numbers to come out of that process. And that's what we've been doing all along. There is something, though. There are two things I want to show you here that we've already begun to play with. Here was our globe tossing example. Let's see if it will waken itself up here a little bit. And when we look at this, we often start with a flat prior. I want to introduce you to a couple of things that will hopefully motivate us. And again, we have crept up on this. There's a machine called a Galton machine or a Chinko machine. Favorite machine in Asia. It's basically a pinball machine. And I'm going to show you a little animation. Here are the pins going across. There's several of them. I think there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 13 pins here. And what happens is a pin, okay, and the ball will go through each of these different gates. I'm going to show you a process by which it happens. And every time it goes through, okay, it'll eventually land in one of these 14 different sockets at the bottom. You can actually make this thing, cork board, and build pins into it. I mean, actual straight pins, and get some little 1/4-inch beads and play with this. I've done it with kids for years. Just is very, not trying to teach them anything except have a little bit of fun. It's basically a pinball machine, and you're always going to get this distribution. You're always going to get this distribution, where there's going to be an inflection point here and here. It's going to be literally pinched in, and it's going to be interesting to see. Okay, let's run it. Okay, here come the pins coming through. Potentially some weird stuff going on with the communications here, obviously. Okay, a little. It's called the Quantile Dot Diagram that's being built down there. This is a physical process. Look, it's always coming up with that. Okay, let's see if it happens again. Okay, another one. Okay, come on, you can get in there. There we go. It's a little stuck. Okay, now it's building up a little bit faster, a little bit faster, a little bit faster. The blue is the city-state Rome wins, and the red is Carthage when, of course, we know that in the history of the Mediterranean, Carthage was razed to the ground and the earth was salted. Yeah, pretty serious about their annihilation there. Okay. Well, whatever's happening with this is real interesting in the background. Let's just shut that down. Oh, come on, you can do it. Come on, keep building it up. See, it's the build up. That doesn't like it. Oop, one more. Then we're going to get rid of this thing. I think it's taking up lots of airspace between. There we go. It's going. Anyways, get the idea that it always will come up with this. Get rid of this thing.